The greatest triumph of civilization is often seen as our mastery of heat. Yet our conquest of cold is an equally epic journey, from dark beginnings to an ultra-cool frontier. For centuries, cold remained a perplexing mystery, with no obvious practical benefits. Yet in the last 100 years, cold has transformed the way we live and work. Imagine supermarkets without refrigeration, skyscrapers without air conditioning, hospitals without MRI machines and liquid oxygen. We take for granted the technology of coal, yet it has enabled us to explore outer space and the inner depths of our brain. And as we develop new ultra-cold technology to create quantum computers and high-speed networks, it will change the way we work and interact. How did we harness something once considered too fearsome to even investigate? How have scientists and dreamers over the past 4 centuries plunged lower and lower down the temperature scale to conquer the cold and reach its ultimate limit, a holy grail as elusive as the speed limit of light? Absolute Zero. Up next on Nova. Extreme cold has always held a special place in our imagination. For thousands of years, it seemed like a malevolent force associated with death and darkness. Cold was an unexplained phenomenon. Was it a substance, a process, or some special state of being? Back in the 17th century, no one knew, but they certainly felt its effects in the freezing London winters.
17th century England was in the middle of what's now called the Little Ice Age. It was fantastically cold by modern standards. You have to imagine a world lit by fire in which most people are cold most of the time. Cold would have felt like a real presence, a kind of positive agent that was affecting how people felt.
Back then, people felt at the mercy of cold. This was a time when such natural forces were viewed with awe as acts of God. So anyone attempting to tamper with cold did so at his peril. The first to try was an alchemist, Cornelius Drebbel. On a hot summer's day in 1620, King James I and his entourage arrived to experience an unearthly event. Drebbel, who was also the court magician, had a wager with the king that he could turn summer into winter. He would attempt to chill the air in the largest interior space in the British Isles, the Great Hall of Westminster. Drebbel hoped to shake the king to his core.
He had a phenomenally fertile mind. He was an inventor par excellence. His whole world was steeped in a world of alchemy, of perpetual motion machines, of the idea of time, space, planets, moon, sun, gods. He was a fervently religious man. He was a person for whom nature presented a a galaxy of possibilities.
Dr. Andrew Shidlow, a chemist with a lifelong fascination for Drebbel, enjoys his reincarnation as the great court magician. Like most alchemists, Drebbel kept his method secret. Dr. Shidlow wants to test his ideas on how Drebbel created artificial cold.
When Drebel was trying to achieve the lowest temperature possible. He knew that ice, of course, was the freezing point, the coldest you could get normally. But he would have been aware of the fact, through his experience, that mixing ice with different salts could get you a colder temperature.
Salt will lower the temperature at which ice melts. Dr. Shidlow thinks Drebel probably used common table salt, which gives the biggest temperature drop. But salt and ice alone would not be enough to cool the air within such a large interior. Drebel was famous for designing elaborate contraptions, a passion shared by Dr. Shidlow, who has an idea for the alchemist's machine.
So here we would have had a fan which would have been turned over, blowing warm air over the cold vessels there, and as the air blows over these cold jars, we would have had, in effect, the world's first air conditioning unit.
But could this really turn summer into winter?
The idea is to stir it in as well as possible in the 5 seconds that you have to do it.
Dr. Shidlow stacks the jars of freezing mixture to create cold corridors for the air to pass through.
Right, we can feel it's very cold. In fact, I could feel cold air actually falling on my hands, because cold air, of course, is denser than warm air, and one can feel it quite clearly on the fingers.
The vital question: would the gust of warm air become cold?
Wolf, I can feel certainly a blast of cold air hitting me as that second cover was released. Well, temperature, we're on 14 at the moment. Yes, keep it going. That's definitely the right direction.
King James would have been shaken by his encounter with man-made cold. Had Drebel written up his great stunt, he might have gone down in history as the inventor of air conditioning. Yet it would be almost 3 centuries before this idea would actually take off. To advance knowledge and conquer the cold required a very different approach: the scientific method. The fundamental question, what is cold, haunted Robert Boyle nearly 50 years later. The son of the Earl of Cork, a wealthy nobleman, Boyle used his fortune to build an extensive laboratory. Boyle is famous for his experiments on the nature of air, but he also became the first master of cold. Believing it to be an important but neglected subject, he carried out hundreds of experiments.
He worked through, very systematically, a series of ideas about what cold is. Does it come from the air? Does it come from the absence of light? Is it that there are strange, so-called frigorific, cold-making particles?
In Boyle's day, the dominant view was that cold is a primordial substance that bodies take in as they get colder and expel as they warm up. It was this view that Boyle would eventually overturn by a set of carefully devised experiments on water. First, he carefully weighed a barrel of water and took it outside in the snow, leaving it to freeze overnight. Boyle was curious about the way water expanded when it turned to ice. He reasoned that if once the water turned to ice, the barrel weighed more, then perhaps cold was a substance after all. But when they re-weighed the barrel, they discovered it weighed exactly the same.
So what must be happening, Boyle guessed, was that the particles of water were moving further apart. And that was the expansion, not some substance flowing into the barrel from outside.
Boyle was becoming increasingly convinced that cold was not a substance, but something that was happening to individual particles, and he began to think back to his earlier experiments with air. As matter like air becomes warmer, it tends to expand. Boyle imagined the air particles were like tiny springs, gradually unwinding and taking up more space as they heat up.
Boyle's conclusion here was that heat is a form of motion of a particular kind, and that as bodies cool down, they move less and less.
Boyle's longest published book was on the cold. Yet he found its study troublesome and full of hardships, declaring that he felt like a physician trying to work in a remote country without the benefit of instruments or medicines. To properly explore this country of the cold, Boyle lamented the lack of a vital tool, an accurate thermometer. It was not until the mid-17th century that glass blowers in Florence began to produce accurately calibrated thermometers. Now it became possible to measure degrees of hot and cold. Like the air in Boyle's experiment, heat makes most substances expand. Early thermometers used alcohol, which is lighter than mercury and expands much more with heat. So these Florentine thermometers were sometimes several meters long and often wound into spirals. But there was still one major problem with all thermometers: the lack of a universally accepted temperature scale.
There are all kinds of different ways of trying to stick numbers to these degrees of hot and cold, and they, on the whole, didn't agree with each other at all. So one guy in Florence makes one kind of thermometer, another guy in London makes a different kind, and they just don't even have the same scale. And so there was a lot of problem in trying to standardize thermometers.
The challenge was to find events in nature that always occur at the same temperature and make them fixed points. At the lower end of the scale, that might be ice, just as it begins to melt. At the upper end, it could be wax, heated to its melting point. The first temperature scale to be widely adopted was devised by Gabriel Daniel Fahrenheit, a gifted instrument maker who made thermometers for scientists and physicians across Europe. He had several fixed points. He used a mixture of ice, water, and salt for his 0 degrees, ice melting in water at 32 degrees, and for his upper fixed point, the temperature of the human body at 96 degrees, which is close to the modern value.
One of the things that Fahrenheit was able to achieve was to make thermometers quite small. And that he did by using mercury, as opposed to alcohol or air, which other people had used. And because mercury thermometers are compact, clearly if you're trying to use it for clinical purposes, you don't want some big thing sticking out of the patient. So the fact that he could make them small and convenient, that seems to be what made Fahrenheit so famous and so influential.
It was a Swedish astronomer, Anders Celsius, who came up with the idea of dividing the scale between 2 fixed points into 100 divisions.
The original scale used by Celsius was upside down. So he had the boiling point of water as 0 and the freezing point as 100, with numbers just continuing to increase as we go below freezing. And this is another little mystery in the history of the thermometer that we just don't know for sure. What was he thinking when he labeled it this way? And it was the botanist Linnaeus, who was then the president of the Swedish Academy, who after a few years said, well, we need to stop this nonsense, and inverted the scale to give us what we now call Celsius scale today.
A question nobody thought to ask when devising temperature scales was, how low can you go? Is there an absolute lower limit of temperature? The idea that there might be would become a turning point in the history of cold.
The story begins with the French physicist Guillaume Amonton.
It's pressure.
He was doing experiments, heating and cooling bodies of air to see how they expand and contract.
Amonton heated air in a glass bulb by placing it in hot water. Just like a hot air balloon, the air in the glass bulb expanded as the increased pressure forced a column of mercury up the tube. Then he tried cooling the air.
He was noticing that, well, when you cool a body of air, the pressure would go down. And he speculated, well, what would happen if we just kept cooling it?
By plotting this falling temperature against pressure, Amonton saw that as the temperature dropped, so did the pressure. And this gave him an extraordinary idea.
Amonton started to consider the possibility, what would happen if you projected this line back until the pressure was zero? And this was the first time in the course of history that people had actually considered the concept of an absolute zero of temperature. Zero pressure, zero temperature.
It was quite a revolutionary idea when you think about it, because you wouldn't just think that temperature has a limit of a lower bound or zero, because in the upper end it can go on forever, we think, until it's hotter and hotter and hotter. But somehow maybe there's a 0 point where this all begins. So you could actually give a calculation of where this 0 point would be. Amonton didn't do that calculation himself, but some other people did later on. And when you do it, you get a value that's actually not that far from the modern value of roughly minus 273 centigrade.
In one stroke, Amonton had realized that although temperatures might go on rising forever, they could only fall as far as this absolute point, now known to be minus 273 degrees centigrade. For him, this was a theoretical limit, not a goal to attempt to reach. Before scientists could venture towards this 0 point, far beyond the coldest temperatures on Earth, they needed to resolve a fundamental question. By now, most scientists defined cold simply as the absence of heat. But what was actually happening as substances warmed or cooled was still hotly debated.
The argument of men like Amonton relied completely on the idea that heat is a form of motion and that particles move more and more closely together as the substance in which they're in gets cooler and cooler.
Unfortunately, the science of cold was about to suffer a serious setback. The idea that cooling was caused by particles slowing down began to go out of fashion. At the end of the 18th century, a rival theory of heat and cold emerged that was tantalizingly appealing, but completely wrong. It was called the caloric theory, and its principal advocate was the great French chemist Antoine Lavoisier. Like most scientists of the time, Lavoisier was a rich aristocrat who funded his own research. He and his wife, Madame Lavoisier, who assisted with his experiments, even commissioned the celebrated painter David to paint their portrait. Lavoisier carried out experiments to support the erroneous idea that heat was a substance, a weightless fluid that he called caloric.
He thought in the solid state of matter, molecules were just packed close in together. And when you added more and more caloric to this, the caloric would insinuate itself between these particles of matter and loosen them up. So the basic notion was that caloric was this fluid that was, as he put it, self-repulsive. It just tended to break things apart from each other. And that's his basic notion of heat. So cold is just the absence of caloric or the relative lack of caloric.
Lavoisier even had an apparatus to measure caloric, which he called a calorimeter. He packed the outer compartment with ice. Inside, he conducted experiments that generated heat, sometimes from chemical reactions, sometimes from animals, to determine how much caloric was released. He collected the water from the melting ice and weighed it to calculate the amount of caloric generated from each source.
I think the most striking thing about Lavoisier is that he sees caloric as a substance which is exactly comparable with ordinary matter, to the point that he includes caloric in his list of the elements.
Indeed, for Lavoisier, it's an element like oxygen or nitrogen. Oxygen gas is made of oxygen plus caloric. And if you take the caloric away, presumably the oxygen might liquefy. So it's a very hard model to shift because it explains so much, and indeed Lavoisier's chemistry was so otherwise extraordinarily successful. However, Lavoisier's story about caloric was soon undermined.
But there was one man who was convinced Lavoisier was wrong and was determined to destroy the caloric theory. His name was Count Rumford. Count Rumford had a colorful past. He was born in America, spied for the British during the Revolution, and after being forced into exile, became an influential government minister in Bavaria. Among his varied responsibilities was the artillery works. And it was here in the 1790s that he began to think about how he might be able to disprove the caloric theory using cannon boring. Rumford had noticed that the friction from boring out a cannon barrel generated a lot of heat. He decided to carry out experiments to measure how much. He adapted the machine to produce even more heat by installing a blunt borer that had one end submerged in a jacket of water. As the cannon turned against the borer, the temperature of the water increased and eventually boiled. The longer he bored, the more heat was produced.
For Rumford, what this showed was that heat must be a form of motion, and heat is not a substance, because you could generate indefinitely large amounts of heat simply by turning the cannon.
Despite Count Rumford's best efforts, Lavoisier's caloric theory remained dominant until the end of the 18th century. His prestige as a chemist meant that few dared challenge his ideas. But this did not protect him from the revolutionary turmoil in France, which was about to interrupt his research. At the height of the Reign of Terror, Lavoisier was arrested and eventually lost his head.
Once he was guillotined, his wife left France and eventually met Rumford when he moved to Western Europe in the early 1800s. Rumford then married her, so he'd married the widow of the man who'd founded the theory that he'd destroyed.
The marriage was short-lived. After a tormented year, Rumford left Madame Lavoisier and devoted the rest of his life to his first love, science. It would be nearly 50 years before Rumford's idea that temperature is simply a measure of the movement of particles was accepted. With heat, the particles, what we now know as atoms, speed up, and with cold, they slow down. Rumford's dedication to science led him to become a founder of the Royal Institution in London, and it was here that the next major breakthrough in the conquest of cold would occur. Michael Faraday, who later became famous for his work on electricity and magnetism, would take a critical early step in the long descent towards absolute zero when he was asked to investigate the properties of chlorine using crystals of chlorine hydrate. This experiment was potentially explosive, which is perhaps why it was left to Faraday, and perhaps also why Dr. Andrew Shidlow is curious to repeat it today.
We are about to undertake an exceedingly dangerous experiment in which Michael Faraday in 1823 heated this substance here, the hydrate of chlorine, in a sealed tube. Is that sealed?
That's sealed, Andrew.
That's absolutely brilliant.
In the original experiment, Faraday took the sealed tube and heated the end containing the chlorine hydrate in hot water. He put the other end in an ice bath. Soon he noticed yellow chlorine gas being given off.
Because a gas is being produced, pressure's building up. Ray, this is where it starts to get dangerous. So if you now take a few steps back.
When Faraday did the experiment, a visitor, Dr. Paris, came by to see what he was up to. Paris pointed out some oily matter in the bottom of the tube. Faraday was curious and decided to break open the tube.
Right, so let's have a look inside here.
The explosion sent shards of glass flying. With the sudden release of pressure, the oily liquid vanished.
And there we are.
Is that what happened?
Yeah, that's exactly what happened. It popped open, glass flew. And can you detect the strong smell of chlorine?
I can now.
Absolutely. Well, he detected the strong smell of chlorine, and this was a major mystery for him.
Faraday soon realized the increased pressure inside the sealed tube had caused the gas to liquefy. And when the tube was broken, the oily liquid evaporated. Just as heat must be applied to evaporate water, he saw that energy from the surrounding air had transformed liquid chlorine into a gas. In a brilliant deduction, Faraday realized that by absorbing heat from the air, he had cooled or refrigerated the surroundings. Michael Faraday had produced cold. Later, he used the same technique with ammonia, which absorbs even more heat. He predicted that one day this cooling might be commercially useful. Faraday took no interest in commercial exploitation. But across the Atlantic, a Yankee entrepreneur had a very different philosophy. Frederick Tudor had a chance conversation with his brother that led him on a path to become one of the richest men in America.
The story goes at the dinner table, they were trying to decide what they had on their father's farm they could make money off of, and certainly there was a lot of rocks, but people weren't going to pay for that. So they came up with the idea of maybe ice, because some areas did not have ice. And it seemed kind of crazy at first, but it paid off.
When Tudor began harvesting ice from New England ponds, he soon realized he needed specialized tools to keep up with the huge demand.
We had the saws, and the saws were improvement over the old wood saws. They have teeth that are sharpened on both sides and set, so it cuts on both the up and the down stroke. The crew could clear a 3-acre pond easily in a couple of days.
Tudor's dream to make ice available to all was not confined to New England. He wanted to ship ice to hot parts of the world, like the Caribbean and the Deep South.
When Tudor first tried to convince shipmasters to put his load of frozen water into the ships, they all refused because they told him that water belonged outside the hull, not inside. So he had to go find other investors to get the money to buy his own ship, and he bought a ship by the name of the Favorite.
New England became the refrigerator for the world, with ice shipments to the Caribbean, the coast of South America and Europe. Tudor even reached India and China. Watching the ice cutters working Walden Pond, Henry Thoreau marveled that water from his bathing beach was traveling halfway round the globe to end up in the cup of an East Indian philosopher. Tudor, who soon became known as the Ice King, began using horses and huge teams of workers to harvest larger and larger lakes as the demand for ice grew. During the latter half of the 19th century, the ice industry eventually employed tens of thousands of people.
Tudor became the largest distributor of ice, and he became one of the first American millionaires. And we're talking about one of his ships going to the Caribbean, giving him a profit of $6,000. Now, this is in a time period when people were earning $200 to $300 a year, the average family. So someone earning thousands of dollars was just inconceivable. And that would be losing 20% of your ice when it got there. There was still huge amounts of profit.
Tudor's success was based on an extraordinary physical property of ice. It takes the same amount of heat to melt a block of ice as it does to heat an equivalent quantity of water to around 80 degrees Celsius. This meant that ice took a long time to melt, even when shipped to hotter climates. What started out as a small family enterprise turned into a global business. Frederick Tudor had industrialized coal in the same way the great pioneers of steam had harnessed heat. By the 1830s, the Industrial Revolution was in full swing. Yet ironically, it was not until a small group of scientists worked out the underlying principles of how steam engines convert heat into motion that the next step in the conquest of coal could be made. Only after solving this riddle of heat engines could the first cold engines be made to produce artificial refrigeration.
How much useful work can you get out of a given amount of heat? By the early 1800s, that had become the single most important economic problem in Europe. To make a profit was to convert heat into motion efficiently, without wasting heat and getting the maximum amount of mechanical effect.
The first person to really engage with this problem was a young French artillery engineer, Sadi Carnot. He thought that improving the efficiency of steam engines might help France's flagging economy after defeat at Waterloo in 1815. Working at the Conservatoire des Arts et Métiers, he began to analyze how a steam engine was able to turn heat into mechanical work.
In steam engines, it looks as though heat is flowing around the engine, and as it flows, the engine does mechanical work. The implication there is that heat is neither consumed nor destroyed. You simply circulate it around and it does work.
Carnot likened this flow of heat to the flow of water over a water wheel. He saw that the amount of mechanical work produced depended on how far the water fell. His novel idea was that steam engines worked in a similar way, except this fall was a fall in temperature from the hottest to the coldest part of the engine. The greater the temperature difference, the more work was produced. Carnot distilled these profound ideas into an accessible book for general readers, which meant it was largely ignored by scientists instead of being heralded as a classic.
Well, this is the book. It's Carnot's only publication, Reflections on the Motive Power of Fire of 1824. A small book, 118 pages only, published just 600 copies, and in his own lifetime it's virtually unknown. 20 years after the publication, William Thomson, the Scottish physicist, is absolutely intent on finding a copy. He's here in Paris, and the accounts we have suggest that he spends a great deal of time visiting bookshops, visiting the bouquinistes on the banks of the Seine, looking, always asking for the book, and the booksellers tell him they've never even heard of it.
William Thomson, who would later become Lord Kelvin, a giant in this new field of thermodynamics, was impressed by Carnot's idea that the movement of heat produced useful work in the machine. But when he returned home, he heard about an alternative theory from a Manchester brewer called James Joule.
Joule had this notion that Carnot was wrong, that heat wasn't producing work just by its movement. Heat was actually turning into mechanical work, which is a very strange idea when you think about it. We're all now used to thinking about energy and how it can take all different forms. But it was a revolutionary idea that heat and something like mechanical energy were at bottom the same kind of thing.
The experiment that convinced Joule of this was set up in the cellar of his brewery. It converted mechanical movement into heat, almost like a steam engine in reverse. He used falling weights to drive paddles around the drum of water. The friction from this process generated a minute amount of heat. Only brewers had thermometers accurate enough to register this tiny temperature increase caused by a measured amount of mechanical work.
Joule's work mattered because it was the first time that anyone had convincingly measured the exchange rate between movement and heat. He'd proved the existence of something that converts between heat and motion. That something was going to be called energy. And it's for that reason that the basic unit of energy in the new international system of units is named after him, the joule.
Joule and Carnot's ideas were combined by Thomson to produce what would later be known as the laws of thermodynamics. The first law, from Joule's work, states that energy can be converted from one form to another, but can never be created or destroyed. The second law, from Carnot's theory, states that heat flows in one direction only, from hot to cold. In the second half of the 19th century, this new understanding paved the way for steam power to artificially produce ice. Ice-making machines like this one were based on principles discovered by Michael Faraday, who showed when ammonia changes from a liquid to a gas, it absorbs heat from its surroundings. It's part of what is now known as a refrigeration cycle. In the first stage of this cycle, gigantic pistons compress ammonia gas into a hot liquid. The hot liquefied ammonia is pumped into condenser coils, where it's cooled and fed into pipes beneath giant water tanks. Then the pressure is released, and the liquid ammonia evaporates, absorbing heat from the surrounding water. Gradually, the tanks of water become blocks of ice. By the 1880s, many towns across America had ice plants like this one, which could produce 150 tons of ice a day. For the first time, artificially produced ice was threatening the natural ice trade created by Frederick Tudor. America's appetite for ice was insatiable. Slaughterhouses, breweries, and food warehouses all needed ice. Animals were disassembled on production lines in Chicago, and the meat was loaded into ice-cooled boxcars to be shipped by railroad.
Livestock on its way to the great meat-packing centers of the nation, to markets everywhere. Food of every sort, safely and quickly delivered in refrigerator cars.
As fruit and vegetables became available out of season, urban diets improved, making city dwellers the best-fed people in the world. And to keep everything fresh at home, the Iceman made his weekly delivery to recharge the refrigerator.
Refrigeration makes a tremendous difference in people's lives. First of all, in the diet, what is possible for them to eat. They can go to the store once a week. They don't have to go every day. They can obtain at that store foods that are from almost anywhere in the world that have been transported and kept cool, and then they can keep them in their own home.
Eventually, the Iceman disappeared as more and more households bought electric refrigerators. These used the same basic principles as the old ice-making machines. Liquid ammonia circulating in pipes evaporates, draining the heat away from the food inside. Compressed by an electric pump, the gas is condensed back into liquid ammonia, and the cycle begins again.
The electric power companies loved refrigerators because they ran all day and all night. They may not have used that much power for each hour, but they continued to use that. So one of the ways that they sold rural electrification was the possibility of having your own refrigerator.
In the early days, the freezer was used to freeze water, nothing else. Freezing was seen as having the same damaging effects as frost. The man who would change this idea forever was a scientist and explorer named Clarence Birdseye. In 1912, Birdseye set off on an expedition to Labrador, and the temperature dropped to 40 degrees below freezing. The Inuit had taught Birdseye how to ice fish by cutting a hole in the ice several feet thick. When he caught a fish, he found it froze almost as soon as it hit the air. This process seemed to preserve the fish in a unique way.
When you went to cook this fish, it tasted just as good as fresh. And he couldn't figure that out because when he froze fish at home, they would taste terrible. So when he got back home, he finally tried to figure out what was the difference between this quick freezing and the usual freezing.
Under closer examination, he could see what was happening to the fish cells. With slow freezing, large ice crystals formed, which distorted and ruptured the cells. When thawed, the tissue collapsed and all the nutrients and flavor washed away. The so-called mushy strawberry syndrome. But with fast freezing, only tiny ice crystals were formed inside the cells, and these caused little damage. It was all down to the speed of the freezing process. A simple concept, but it took Clarence Birdseye another 10 years to perfect a commercial fast freezing technique that would mimic the natural process he'd experienced in Labrador. In 1924, he opened a flash freezing plant in Gloucester, Massachusetts, that froze freshly landed fish at minus 45 degrees.
He then extended that to all sorts of other kinds of meats and produce and vegetables, and almost single-handedly invented the frozen food industry.
Refrigerators and freezers would eventually become icons of modern living. but there was a less visible cold transformation happening at the same time. This would also have a huge impact on urban life: the cooling of the air itself. 3 centuries had passed since Cornelius Drebbel had shaken King James in Westminster. Now, at the dawn of the 20th century, air cooling was about to shake the world.
Tell me, what is the lowdown on this air conditioning thing?
Now you've started something by asking me that.
Air conditioning was about to transform modern life, and the person largely responsible was Willis Carrier, who started off working for a company that made fans.
Carrier is sent to Brooklyn for a very special job in 1902. The company that publishes the magazine Judge, one of the most popular full-color magazines in America at this particular time, is having a huge problem. It's July in Brooklyn, and the ink for which they use on their beautiful covers is sliding off the pages. It will not stick because the humidity is too high. Carrier, using some principles that he's been developing as a young new employee of this fan company, finds a way to get out the July 1902 run of the Judge magazine, and from there he begins to eventually build his air conditioning empire.
It's based on a simple principle.
Control of humidity through control of temperature. That was Willis Carrier's idea.
He used refrigeration to cool the water vapor in the humid air. The vapor condensed into droplets, leaving the air dry and cool. The demand for air conditioning gradually grew. In the 1920s, movie houses were among the first to promote the benefits. People would flock there in summer to escape the heat.
The movies are wildly popular, and the air conditioning certainly helps to attract an audience, especially if they happen to be walking down the street on a horribly hot day and they duck into this movie theater and have this wonderful experience.
Air conditioning became increasingly common in the workplace, too, particularly in the South, where textile and tobacco factories were almost unbearable without cooling.
When employees breathe good air and feel comfortable, they work faster and do a better job.
I think some people think that these were nice, compassionate employers who were cooling down the workplace for the workers, but of course nothing could be further from the truth. That was an inadvertent byproduct, but actually this was a quality control device to control the breaking of fibers in cotton mills, to get consistent quality control in these various industries, to control the dust that had bedeviled tobacco stemming room workers for decades. I think the workers obviously went home and to their unair-conditioned shacks in most cases, and talked about how nice and cool it was working during the day.
It's silly to suffer from the heat when you can afford the modest cost of air conditioning.
By the 1950s, people were air conditioning their homes with standalone window units that could be easily installed. This wasn't just an appliance. It offered a new, cool way of life.
Walking down a typical southern street prior to the air conditioning revolution, you would have seen families, individuals outside. They would have been on their porches, on each other's porches. There was a visiting tradition, a real sense of community. Well, I think all that changes with air conditioning. You can walk down that same street, and basically what you'll hear are not the voices of people talking on the porch, you'll hear the whir of the compressors.
Guess what we've got? An RCA room air conditioner. I'm a woman, and I know how much pure air means to Mother in keeping our rooms clean and free from dust and dirt.
Control of the cold has transformed city life. Refrigeration helped cities expand outwards by enabling large numbers of people to live at great distances from their source of food. Air conditioning enabled cities to expand upwards. Beyond 20 stories, high winds make open windows impractical. But with air conditioning, 100-story skyscrapers were possible.
Technologies emerge which not only worked to insulate human society against the evils of cold, but turned cold into a productive, manageable, effective resource. On the one hand, the steam engine, on the other, the refrigerator. Those two great symbols of 19th century world, which completely changed the society and economy of the planet. All that is part of, I think, what we could call bringing cold to market, turning it from an evil agent that you feared into a force of nature from which you could profit.
The explosive growth of the modern world over the last 2 centuries owes much to the conquest of cold. But this was only the beginning of the journey down the temperature scale. Going lower would be even harder, but would produce greater wonders that promise extraordinary innovations for the future. With rival scientists racing toward the final frontier, the pace quickens and the molecular dance slows as they approach the holy grail of cold, absolute zero.
On NOVA's Absolute Zero website, enter a virtual lab and see how close you can get to absolute zero. Make your own temperature scale and more. Find it on pbs.org. To order this NOVA program for $24.95 plus shipping and handling, call WGBH Boston Video at 1-800-255-9424.